Today we are going to talk about the 1H NMR spectra of inorganic complexes. So in the inorganic complexes, we have a TMS, it is a reference solvent in NMR spectroscopy. So that peak comes at 0 ppm. So for organic complexes, means like organic compounds, we mostly see the peaks from the 0 to positive region. Whereas for inorganic complexes, we see from the 0 to minus 50 ppm. Okay, so for organic compounds, we see in the positive region. For inorganic complexes, we see in the negative region. So what is the reason here? So because here, so this is the NMR spectroscopy, so this can be useful to predict whether hydrogen is directly attached to the metal or not. Okay, so for that purpose, this NMR spectroscopy we can use, and later I will explain where hydrogen is not here. Hydrogen is a part of the metal complex, but it's not directly attached to the metal, and where in those cases how the chemical shift values will vary. So first we will see where hydrogen attached to the metal directly. So in this case, what will happens, the electronegativity of hydrogen is greater than metal. So because of that reason, the electron density, whatever electron density is there with metal, that will be goes on to the hydrogen. So hydrogen will become more shielded. So that is the reason why we are seeing a hydrogen between a 0 to minus 50 ppm. So we cannot say 0 is minus 3 to minus 50 ppm. Okay, and here hydrogen is present as a hydride, H minus. From there itself we can conclude that it's having more electron density. Because of that, we are seeing this chemical shift value from minus 30 to minus 50 ppm. So now we'll see the few examples. The first example we have here, hydrogen, rhodium, CN5, minus. Okay, so here we'll see the spin of rhodium is 1 by 2. Because I of rhodium is 1 by 2. Okay, so now if we see the NMR spectra of this complex, we'll get a doublet. We'll see a doublet. So how that doublet came, we'll see here. So here only one hydrogen is there, so there is no another hydrogen, so only one peak we will get for one hydrogen. Okay, this is for hydrogen. So now rhodium is spin active, so rhodium spin is 1 by 2. So this hydrogen couples with this rhodium, this hydrogen couples with this rhodium. So we have a principle to Ni plus 1 to Ni plus 1. So according to that, 2 into 1 into 1 by 2 plus 1. So we'll have a doublet here. So N means number of nucleus, I is a spin number. So here we have only one rhodium, so we're having spin of 1 by 2. So this hydrogen couples with rhodium, and it gives a doublet. So this is because of the hydrogen rhodium coupling. Okay, so this peak we get at minus 10 ppm. This peak will get at minus, imagine this is the TMS 0, so this peak will get at minus 10 ppm. So from here we can conclude that hydrogen is directly attached to the metal. So wherever you will get the hydrogen chemical shift value in the negative region, so there we can conclude that hydrogen directly attached to the metal. And we'll see next example. We have hydrogen, rhodium, P, Me2O, 4 times Cl plus. So this is the next complex here we have. So before going to the identify how many peaks we will get, first we will draw the structure for this complex. We have rhodium here. This is the octahedral complex. O P Me2 OPMe2. The structure looks like this, and here hydrogen and here chlorine. Now, so here also it's very simple to predict how many peaks we will get. See, here only one hydrogen is there, so for that one hydrogen we will get a singlet, and for the this hydrogen couples with this rhodium spin. This rhodium is having spin of 1/2, so 1/2 means you will get a doublet. This is because of hydrogen and rhodium. Okay, next, so here we have phosphorus also. 4 phosphorus we have. So phosphorus also spin active. The spin of phosphorus is 1/2. So total 4 phosphorus are there. So we use 2Ni+1 principle. So how many phosphorus? 4. 2 into 4 into 1/2 plus 1. So 2 get cancelled. So we'll get 5 peaks. So each doublet again splits into 5 lines. Okay, so final spectra looks like this. 2 5-line signal we will get like this. So it's very simple here, no need to get confused. So initially we are getting a singlet. That singlet is for hydrogen, because only one hydrogen is there. For that we will get a singlet. If 2 different hydrogens are there, here itself we will get a doublet. Okay, so we have a one singlet for one hydrogen, and for the rhodium also spin active. So this hydrogen couples with this rhodium, because the spin is 1/2, we will get a doublet. This is for the hydrogen and rhodium. And for the same hydrogen, not rhodium, same hydrogen is coupled with phosphorus. So this is for the hydrogen and 31p. Same hydrogen is coupling with phosphorus also. So how many phosphorus are there? 4 phosphorus are there. So each phosphorus is having spin of 1/2. So for that, if we use 2Ni+1, we will get 5 line. So now each doublet is split into 5 line. So final spectra of this one having 2 5-line signals. Okay. So in examination point of view, they may ask how many lines this compound is having. So we can say that 2 5-line signals. Next complex we have here, third one, HMnCO5. Okay, so here only one hydrogen is there. For that one singlet we will get, one single peak we will get, and manganese is spin active. The spin of manganese is 5/2. If we use that 2Ni+1 line, we will get 6 lines. So the spectra of this compound includes a 6-line signal. This is about this complex. And we have fourth example, that is HCO4. Okay, the spin of cobalt is 7/2 here. So we'll get a single line for hydrogen. So for this couples with 7/2 spin, so we'll get an 8-line signal here. So this complex it shows 8-line signal in NMR spectra, and this complex shows 7-line signal in NMR spectra. So like that we can do for other things also, like what can you say, right? We can take HCOCN5 3-. So here also we'll get 8 lines, because the spin of cobalt is 7/2. Next, so this NMR spectra we can use to predict the structure also, structure of complex. How NMR spectra useful in predicting the structure of a particular complex? Let's say we have a complex H Ni O P E T 3. This 4 times. So this is the complex. The NMR spectra of this complex gives one 5-line signal. 5-line spectra we'll get. So if we record NMR for this complex, we'll get a 5-line signal, 5-line spectra. But here there are two possibilities are there in the structure wise. So it can exist in trigonal square pyramidal like this. This is OPET3, OPET3, and hydrogen. And this is the one possibility. And the second possibility is it can exist in a trigonal bipyramidal shape also. PET3, OPET3, and hydrogen. So now we will see where in which structure we are getting a 5-line signal and which structure we are not getting a 5-line signal. So first we will go for the trigonal bipyramidal, because most of the 5 coordination will exist as a trigonal bipyramidal. I hope this could be the correct answer. So here we have a single hydrogen, so for that we will get a single line. Okay, and further, so this hydrogen, nickel is not active, this is not active, so this hydrogen has to couple with the phosphorus. Okay, so here there are 4 phosphoruses are there, but out of 4, 3 are equivalent and 1 is unequivalent. This is a equatorial, this is equatorial, and this is also equatorial, but this is axial. So all 4 are not same, so they are different. Okay, so now what will happen, since 2 phosphorus is there, we'll get a doublet here. For 2 different phosphorus we'll get a doublet, and further this hydrogens couples with these 3 equatorial phosphorus. So we can use 2Na+1 principle, so we will have a 1 4-line signal here, and one axial phosphorus, so that will be a doublet. So if we are assuming that this exists in the trigonal pyramidal shape, trigonal bipyramidal shape, it has to show 1 4-line signal, one 2-line signal in the spectra, but this is not showing this spectra. This is showing only 1 5-line spectra. So now we'll go for this. So here all phosphoruses are same. Okay, we have a single line for hydrogen, and now this will couple with 4 phosphorus atom. 4 phosphorus means 2Na+1, that means 2 into 4 into 1/2 plus 1. So we have a 5-line. So this further splits into 5-line. So from here we can conclude that this complex HNI POPET3 4 times will exist as a square pyramidal, not as a trigonal bipyramidal. Okay, so here don't get confused. So here we have a single line for hydrogen, and there are 2 different phosphorus we have. One is axial phosphorus, another one is equatorial phosphorus. So for those 2 phosphorus we will get a doublet. This singlet further splits into doublet, and further there is a coupling there is coupling with 3 equatorial phosphorus, and 1 axial phosphorus. After coupling with the 3 phosphorus, we will get 1 4-line signal. Here we will get the 1 2-line signal. So the spectra looks like this. 1 2 3 4. If we assume that it exists in trigonal pyramidal structure, it has to show this spectra, but this is not acceptable. So this is acceptable. A 5-line signal will get here. So by this way we can also predict the structure of the complex by using NMR spectroscopy. I hope it's clear. And next example we have, here we have H or U C5H5 twice. So here here a new concept will come, that is called wedging. Wedging means this we can see only in case of cyclopentadienyl compound. So when it attached to a metal, okay, we can see three different protons. This is HA proton, HB, this is also HB, and this is HC, and this is also HC. But because of this wedging concept, wedging means nothing but a rotation about the axis. So this cyclopentadienyl will rotate along the axis. Because of that wedging, so we cannot differentiate which is we cannot differentiate different kinds of protons. So instead of three different protons, because of this wedging concept, we will get one broad singlet. Okay, so wherever cyclopentadienyl attached to a metal, so there we will see this wedging concept. Because of this wedging concept, we will get a broad singlet. And if we see the spectra of this complex, so it looks like this. So this is the TMS peak, and this is the one broad singlet, and another broad singlet is here. So from here we can easily identify which peak is correspond to what. So as I said, this is 0, and this is negative region, and this is positive region. Okay, so as I said that when hydrogen attached to a metal directly, the chemical shift of that hydrogen will be in the negative region. So that means this is for hydrogen and this is for cyclopentadienyl. And another thing we need to know here, that is generally these protons comes around 6 to 5 to 7 ppm, but here it's coming almost equals to the almost near to the TMS, because here we can talk about the back bonding concept. So there is electron density transfer from the metal to cyclopentadienyl ring. So because of that reason, what is happening, the cyclopentadienyl signal is getting upfield shift. So this is about this complex. And next we have platinum AC twice. So this exists in a square planar shape. Okay. So now here in the NMR spectra, we have two different protons here. Methyl protons, total 12 methyl protons, and this is double bond here, and 2 CH proton. So we can get a 2 peak here. So this is for TMS, and we'll get a 2 peak for 2 different protons in the ratio of 1:6 ratio, because 6 is for the methyl groups and 1 is for the CH groups. And here it's clear that, see, wait a minute, in this case this hydrogen came in the negative region, but whereas here these hydrogens are coming in the positive region. So because it's clear that here hydrogen is directly attached to the metal, but here it's not directly attached to the metal. So because of that reason we got a peak in the positive region. Okay, by the, like this also we can identify whether hydrogen is directly attached to the metal or not. So if it is directly attached to metal, we'll get a negative region chemical shift value. If it's directly attached, we'll get a positive region. If it's not directly attached, we'll get a positive. And another thing we have here, just a salt, not just salt, kind of just salt. We have platinum here, hydrogen, sorry, ethylene, and this chlorine, and it attached to the pyridine. It exists there. So in this case, we will get how many lines we will get? Here we will get one line, and this is second, and this is third. So we will get a 3-line signal here. And if you see this one, ethylene, generally it comes around 4.5 to 5 ppm. But in this case, it's directly attached to the metal. So because of that reason, this value will be upfield shifted. This chemical shift value will be upfield shifted compared to normal ethylene molecule. So this is about this complex. And next we have this question. I think they have asked before in a CSL exam. C6H6 MoCO3. So the complex structure looks like this. Okay, so here also we can see the concept of wedging. So because of the wedging, so these all protons will be gives only one proton, so we'll get a singlet here. And next we'll go for the diborane. It's very important. We have a diborane. So the diborane structure looks like this. So in this structure we can see two different hydrogens, terminal hydrogens and bridged hydrogens. Okay, so if we record NMR spectra for diborane, initially we will get a 2-line signal because two different protons are there, bridging as well as terminal. Okay, so now see the terminal attached to the only one boron. The spin of boron is 3/2, whereas bridged attached to 2 borons. So when this terminal is coupled with only one boron, and further it splits into 4-line signal, because 2 Na plus 1, 2 into 1 into 3/2 plus 1 will have a 4-line signal here. Whereas this bridged one, see, bridged one is attached to 2 borons. So 2 into 2/2 3/2 plus 1 will be a 7-line signal. So this will be having a 7-line signal. Okay, so the spectra includes one 7-line signal and one 4-line signal. So 4-line signal is for the terminal hydrogens, and 7-line signal is for the bridged hydrogens. So this is about the diborane. And there are some other examples are there. I will make another video for that. I hope up to now everything is clear. If you have any doubts, you can write in a comment box. Thank you.